Hello, everybody. Happy Thursday. If you are not already doing so, please tell me, dogs or cats, in the chat. What is the answer to that question for you? And otherwise, just wondering how everybody's doing. How you doing?
I'm tired. I had like 2 tests today.
Is it that time of year where we're having tests a lot of all at the same time?
Yeah.
Yeah. That sucks. At least it's over with. Other people were nodding like they're good. What else? How are you doing?
I stayed up until midnight last night with my spectroscopy lab, so that was neat.
Okay. Is this for this class?
No, for astronomy.
Okay.
Yeah, you
Yeah,
slept?
I was up until about
Spectroscopy is
2.
a really good reason to stay up late. What'd you say, Sam?
I was up until about 2 working on this class and medical.
You're welcome.
I was up until about 1, but that was because I had computer issues I was trying to fix.
Those always take forever.
Well, it didn't fix. I'm going to have to try something else.
Well, you don't have any exams from this class this week, at least. All right, let's get back to some physics, or math, I guess, actually, right now. Okay, so we left off talking about histograms last time. We answered the question, what is a histogram? We also talked about different kinds of histograms. We have bar histograms and we have bin histograms. So let's review that. So yeah, first of all, histogram answers the question, how many of each category are there? And so it makes sense to have a histogram in the first place if you're counting, doing a counting experiment and counting different categories of things. So histogram then would make sense, like we used for exams and like this person used for, customer service information. So let's review the difference between a bar histogram and a bin histogram. Sorry. A bar histogram is going to have percentages or fractions along the y-axis, and the population of all of the things in the graph should add up to 100%, or add up to 1 if you're thinking in terms of fractions. So let's review. We have some number of bins, in this case 1, 2, 3, 4, 5, 6, 7, 8 bins. And we are separating our counts into those categories. F sub k, this quantity here that's shown, is the, fraction of results in that bin. And n sub k is the number of results in the bin. So F sub k, that fraction, times the total n, is going to give you the number of results in that bin. And we end up with this expression. And then F sub k is going to be the height of the bar in your bar graph. So all of those percentage heights, 12% plus 8% plus 28%, that are all shown in this sum here, those add up to 100%. And that is our normalization condition for a bar histogram, they all have to add up to 1 or 100%. All right, so then we can also use this bar histogram framework to find the average value in our histogram pretty easily. So we basically take the percentage or fraction of items in the bin and multiply by the value of that bin. So these are average values here. For the first bin, we have the average value of 1.5. For the second bin, we have the average value of 4.5, and so on and so forth. So the average value for the bin, as far as the width dimension, is multiplied by the height for each bin, and multiplied and added together, excuse me, to get that average value in the population. So we're multiplying basically the width times the height here and adding them up for those bins. Okay, questions so far? Bar histograms. Okay. Bin histograms are different because the width is now a kind of like a variable. In the past, in this previous idea of a bar histogram, the width of all these bins is the same. For a bin histogram, however, the width does not have to be the same for all of the bins. And obviously the height doesn't either for either type of bin or bar histogram. Those are going to vary. So in bar histograms, we only care about the height, and the width is like given or inherent to the problem. And in bin histograms, we care about the height, f sub k, and the width of the histogram, delta sub k, for each bin. So instead of the previous math, we're going to take the width of our histogram, of our bin, and multiply by the height of the bin to now get this value f sub k. And when we add up all the f sub k's, basically the area of each bin, the areas should add up to 1 for the bin histogram. And then it's still true that the value per bin times that bin area is going to, and if you multiply those and add them up, you'll get that average value, just like for the previous histogram. So if it turns out you have a bin histogram where all the widths are the same, you pretty much have a bar histogram. But a bin histogram can have bins of different widths. Let's see an example here. So here's a bar histogram example. We have a whole lot of people, 198 students in an intro biology class. And they have an exam here, and this is showing us the exam scores on this histogram. And of course, we have fractional values on the y-axis for our bar histogram. And, some population of students got A's and some population got B's and so on and so forth. So we see those fractions here. 25% roughly for the 50 to 59 range, for the F 50 to 59 range. And 27 students, or 13%, 13.6, 14%, got within the 40 to 49 range for the F. So this, sorry, I keep changing the slide by accident. The the bar histogram here shows the fractions of each category for the number of students. And since this is a bar graph or histogram, the width of each of these bins is the same. From, you know, about 9 points, except for the last one's 10. Now, a bin histogram is going to allow us to have bins of different widths. Let's try to convert our bar histogram into a bin histogram. That's what we're going to do here first. We're going to keep the 10 bins for now. And we're going to let that bin width be 10 or 9, whatever, roughly 10. And we're going to draw our bin histogram now so that the width of the bin is taking up, you don't have to do it this way, but the width of the bin is representative now of of a certain amount of points and not just like I'm in this category, just like a number in this category. So the bin histogram doesn't really look that different from the bar histogram if we keep our bins the same as before. We keep the 10 bins and arrange everything like we did before. The bin histogram looks pretty much like the bar histogram. Okay, we can also consider a bin histogram with bins of differing widths. So we can take all of the 0 to 59 scores and put them in a single category, making that bin width different from the 60 to 69 D category and 70 to 79 C category and 80 to 89 B category and so forth. So this histogram looks significantly different now compared to the one before, where the bin widths were the same. Okay, so what is the advantage or disadvantage of one or the other? With bins of the same width, as you have more and more measurements and thinner bins, this is going to look more and more like a distribution function that we're going to talk about in just a minute. But that's a lot harder to model with the differing bin sizes shown here. However, if you're just trying to get across the point that, look, there's a lot of Fs, this is a good way to do that. You know, if you're trying to really emphasize the largeness of a category, you can do this with bin histograms with differing widths. Sorry, I'm going to plug in. Okay, questions about histograms? Bin histograms, bar histograms. I don't think we have questions. Okay, so we're going to look at, on week 6 here, there's this mean and standard deviation in class problems link for 225 for today. I would like you to go to your breakout rooms and please just do number 1 from that Word document. So it's an example of making some histograms. I'll put that up on my screen so you can get started on it. And then we'll go into breakout rooms. put that back up in just a second. Can't do breakout rooms while. Okay. Breakout rooms are, wait a minute, that work? Okay, I think that worked.
Am I assigned the right room?
I don't know if anybody is.
Got put
I'm gonna
in the-
I'm gonna do that again. Sorry.
Yeah, everyone came.
Everybody's coming back. Okay, people. Hope you had enough time. It's time. Tried to give you plenty of time. I actually did the problem just now as well. So does anybody have some histograms they can show me? Show us. Okay, I see Alex's. Yeah, that looks sort of like mine. Who else has some histograms? Yep, that looks like mine. Thank you, Henry. Okay. Maybe you're all holding up, but I can't see them. Yeah, okay. Yeah, people look like they have similar histograms to me. I'm gonna turn off my background so you can see mine. Using room. All right. So the first histogram has lots of ups and downs. I organized my bins so that they have width of 1 and they start at 70.5 and end at 71.5. Start at 71.5, end at 72.5. Start at 72.5, end at 73.5. And if we fill in the histogram with the numbers given, it looks like this for part A. For part B, we are supposed to redraw now with a bin width of 2 instead of 1, but still starting at 70.5. So now we have a bin width of 70.5 to 72.5 and 72.5 to 74.5 and so on and so forth. And now the histogram is more smooth, you could say, which means there's just less ups and downs. This has a lot more ups and downs. This seems to follow like a 1 up and down kind of trend here. So how you choose your bins definitely is going to affect, you know, how your histogram looks and if you can fit that histogram or not, which is our next topic. Okay, everybody for doing that. All right, so back to talking about histograms. We have a reason we're talking about them that we haven't quite gotten to. Like, why do we care about histogram in the first place? Oh, wait, first I have a histogram warning. And it kind of follows what we were just seeing with this problem we just worked. How you choose your bins really is going to affect how your graph looks. So if you have way too many bins, it just spreads everything out and you can't really see, any kind of trend. If you have too few bins, it just looks like a blob with no definition. It's just like basically like 1 bar in your graph or 2 bars. That doesn't tell you much. So you got to be careful about too many or too few bins, and you can always just try different sizes and see how it looks to try to communicate what you're trying to communicate to your reader. I don't know if y'all can hear me, but it
Zane,
looks
you're the
like my,
professor cut off.
yeah, sorry. Okay. Sorry, I was muted. Why do I care about histograms? Does anyone know?
So we can analyze data trends.
Okay, yes. Why else do I care about histograms? Or like, how exactly can I analyze those data trends?
It's helpful to compare one piece of data to another piece of data.
Okay. So far we've been like talking about, you know, number of people who got A's on a test, or number of people who are wanting to wait for 5 minutes on a phone call. Like, how does this relate to physics though? Like, you know, in physics, we have this method where we take data, we analyze the data somehow in a methodical way to extract information from that data.
Does it help determine an exact value? So like,
How do we do that?
So like depending on where like the peak of the histograms, I guess. Does that
Maybe.
make sense?
Yeah, it might also
That's
depend
like-
on the width of the histogram too,
Oh yeah.
and
yeah.
other factors. But yeah, we're getting closer. So let me just continue with my slides here. How is this relevant? Okay, so when you do an experiment, you make measurements, and the more measurements you take, the more your histogram is going to look like curves instead of rectangles. You take a whole lot of data, you're not going to have these like weird up and down peaks if you choose your histogram bin width correctly also. As you increase your measurements, you can decrease your bin widths because you have so many measurements. And then you should be getting like, you know, sort of the same trends if you have a systematic, you know, a system where you expect a certain trend, that trend should be happening throughout your experiment. And so that's going to become like a continuous curve. And what we can do with a continuous curve is a curve fit. Curve fit. And then, like John was saying, we can extract that information from that curve fit, just like we've learned about before. So we can think of like the tops of the bins as our data points, and our curve is going to be some, what we call a distribution function that we fit to that histogram. So we're getting back to the curve fit. This is all bringing us back to the curve fit, which is like a huge feature of this class and science in general. So questions so far about that, or comments? Okay, I have some examples to show you. I just did like a Google search of histograms and distribution functions. And like, here's an example of a distribution function with not a whole lot of data points, you know, but if we look at the one next to it, data points meaning like a lot of total number of measurements taken. Obviously, there were more measurements taken here, and we have thinner bins here. And so there is more of like a continuous-ish looking kind of trend for this histogram that happens to have two peaks. Another one is here. This histogram has a whole lot of bins and a very, very, very continuous looking curve at the top of all those bars. Sorry. And this has actually been fit already with a curve. That red line there, or red curve, is a fit to that histogram. All right. Now, once we have enough bins for a histogram, we can sort of extrapolate or think of it as a continuous thing. And when we do that, we call that a distribution function. So on this slide, we have the bin histogram equations we already learned from last time and from reviewing today. And then we have a corresponding continuous distribution function version of that quantity for our more like discrete histogram version. So we have here, this was the height, the area basically of each bin. And so we can also get a sort of an amount of that quantity, but in terms of an integral. And when we talk about distribution functions, we frequently are describing a probability that something will occur. We might be talking about the number of events that already occurred, but we could also be talking about a probability that those events will occur. And those are literally the same thing in quantum mechanics. So just mentioning that really quick. All right, and then we have our normalization condition for our bin histogram over here that I'm circling. The normalization condition for the continuous version is going to be here. If we add up all the little heights of our bins, we're going to get 1. Should get 1, or 100% still. All right. Okay, we have this average value, mean value calculation for a population of n things, or using our bin histogram framework. So either of those is going to give us that mean value. We can also find the mean for a continuous distribution with an integral over here. Okay, and then lastly, we have the standard deviation of our discrete system. And we can also find the standard deviation of our distribution. And they are equivalent. The one on the left is just for a continuous function, or for a histogram with a whole lot of numbers, like where n is really huge and your bins can be very small. And then at that point, it's basically like your histogram, the limit of your histogram, or the histogram can be thought of as a distribution function literally, because your bin width becomes so small that it's like a dx, like infinitesimally small. Okay, questions about any of these connections between distribution functions and bin histogram stuff? Okay, we're going to keep going. Now, what about this Gaussian mess we keep hearing about? What is this Gaussian business? The Gaussian curve, also known as the normal curve, normal or Gaussian distribution function, is also known as the bell curve. It has all these names. They're synonyms for each other. And the main feature is this right here, this equation I'm circling. E to the minus x squared. You don't even have to have that over 2 sigma. That's just a constant. So e to the minus x squared with a constant up here, like e to the minus like alpha x squared, you can think of it that way. As long as it has that function, as long as we have that function, we have a Gaussian. And as long as we're not adding something to that, it's going to be centered at x equals 0. So the peak is going to be at x equals 0. And at that peak, the height is 1. Because if you substitute 0 for x here, you're going to get e to the 0, which is 1. So the height of your Gaussian is 1, if this is our function written like this. If we have a constant out front, the height would change. Or if we added a value with outside the e, like e to the minus x squared over 2 sigma squared plus 3. We're just talking about the basic function here that's without being modified. So it has a width parameter of sigma. And so that's if we do have a constant that is 1 over 2 sigma squared up here, then the width parameter of our Gaussian is sigma. And there's just a couple of examples of Gaussian curves over here to the right. You can see a histogram that's been drawn for this photometric study of the young open cluster NGC 3293. So the y-axis and the x-axis here result in a histogram that is small out here, gets big, and then falls back down, and seems to follow a Gaussian curve. So the person studying this put a fit of a Gaussian on there, and it does seem to correlate very well based on the picture. A lot of common systems are modeled by Gaussian distribution functions, because when you measure things that are natural, sometimes you're going to measure the most of the time you're going to measure the most probable value, and then you're going to measure the less probable value, and then there's going to be less chance you'll measure these values out here, and the trend, the probability that you measure the most likely category compared to the least likely category in natural systems is often Gaussian, can often easily be modeled by a Gaussian. So that's why you've heard about it a lot. All right, one more thing I want to mention. This is for, in general, how do we normalize a distribution function? Because we just said, okay, here's this Gaussian, it's not normalized. And we've been working with normalized histograms, and so it's also good to work with normalized distribution functions. So how do we do that? To normalize a distribution function, you force it to equal 1, basically. You say 1 equals this constant times integrating from negative infinity to infinity across your entire axis of your independent variable. And then to solve this integral, to find what a is, we use an integral table. I'll show you that really quick. I think I still have it up here. Nope. Okay. Well, anyway, you use a histogram, you use an integral table to find the solution for this. I'm sorry. To find the solution for that integral there. Okay, so it turns out that that solution is basically equal to sigma times the square root of 2 pi. You can look that up in an integral table and verify that. But the integral shown here that I am boxing with my mouse is equal to sigma times the square root of 2 pi. So A is equal to 1 over sigma times the square root of 2 pi. And now I can substitute this for A in my distribution function, and it is now normalized. So we like to do that so we can compare one distribution function to another easily without dealing with like how much is the y-axis. It's just always a percent or always a fraction, easily comparable to other fractions and other percents. Questions? Anybody? Questions about any of that? Okay, we're going to talk more next week about Gaussian distribution functions and other distribution functions. And we will have to just wait until then to hear more. I'm so sorry.